In this video, we are going to derive frequently used properties that arise from the transport theorem and describe position, velocity, and acceleration of a point in commonly used coordinate systems. So the first part of this video is properties that arise from the transport theorem. The first of these properties is what's called addition of angular velocities. So it's kind of a rule that we're going to be deriving here. And in order to do that, we're going to start as follows. Let A, B, and C be distinct reference frames. And let B be a vector. And we know from the transport theorem that the rate of change of B in frame A is equal to the rate of change of B in frame B plus the angular velocity of B in A crossed with B. And we also know that the rate of change of B in frame B can be related to its rate of change in frame C by a second application of the transport theorem. And what we're going to do is we're going to substitute the second result into the first result. And by doing that, we obtain the following result, which is that dB dt in A is equal to dB dt in C plus omega CB crossed with B plus omega BA crossed with B, which is equal to dB dt in C plus omega BA plus omega CB crossed with B, where I've just reversed the order and factored out the vector product with B. And we also know, so we'll finish this result, we also know that the rate of change of the vector B in frame A can be directly related to its rate of change in frame C through the transport theorem from reference frame C to reference frame A. So that gives us the rate of change in between frames C and A. Now you'll notice that now I have two expressions for the rate of change of the vector in frame A and its relation to the rate of change in frame C, from which I actually get the following result, that omega CA is equal to omega BA plus omega CB. This last result is known as addition of angular velocities. And it can be extended to as many frames as you want. For example, if I added a frame D, I could say omega dA is equal to omega BA plus omega CB plus omega DC. And then you can keep doing this for as many frames as you happen to have. I mean, you could in principle wind up happening, you could have several frames, and you could be adding angular velocities of the frames pairwise. So anyway, so that's the first property. The second property is more of a definition than it is really a property, but it's important. It's called angular acceleration. and it comes up frequently as well. So we define angular acceleration by the symbol alpha. So alpha BA is the angular acceleration of reference frame B as viewed by an observer in reference frame A. And it's actually defined as the rate of change in reference frame A of the angular velocity between frames B and A. Now you'll notice something about this quantity. Let's suppose that I apply the transport theorem to omega BA. So I'm going to denote this as follows. Now apply the transport theorem to the vector omega BA. And look what we get. We get that the rate of change in frame A of omega BA is equal to its rate of change in frame B plus omega BA crossed with omega BA. But we know that omega BA crossed with omega BA is 0 because any vector, the vector product of any vector with itself is 0. So that term drops out. And we get that the rate of change of omega BA in frame A is the same as the rate of change of omega BA in frame B. And that may seem like a somewhat surprising result, but it basically says that the rate of change of the angular velocity between two frames is the same regardless of whether you're taking the rate of change in the first frame or if you're taking the rate of change in the second frame. So the result that I get here is that alpha BA is equal to d dt in A of omega BA, which is also equal to d dt in B of omega BA. Now the third thing is we're going to be describing the relationship between angular velocity between two frames and the opposite of that angular velocity. So really what I'm looking for here is the relationship between omega BA and omega AB. That's the next thing. So we know that the angular velocity of any frame in relation to itself is 0. Frame can't rotate relative to itself. So therefore, I can write the following, that omega AA from the addition of angular velocity rule is equal to omega BA plus omega AB. What I actually did here was everywhere I saw C in this equation, I replaced it with an A. So that's C being replaced with A in the addition of angular velocity rule. So if I take that result, I know that that has to equal 0. So given the fact that that has to equal 0, I know that omega AB has to equal negative omega BA. So that's the third property that I needed to define. Now that we have these properties defined, we can actually start describing position, velocity, and acceleration, and we're going to need these properties in order to be able to parameterize that motion in different reference frames. In different coordinate systems. So we're gonna wind up using these results quite frequently. So the next topic is going to be position, velocity, and acceleration of a point. Now, what's important in this discussion is as follows. I'm going to start with the following setup. Let A be a reference frame. And let O be a point fixed in A. So this picture looks like this. Here's a reference frame. There's A, and there's a point O. And O is fixed in A. O is fixed in A. And then I'm going to say let P be an arbitrary point. So there's P, some arbitrary point. And I'm going to draw the vector from O to P, and I'm going to call that vector RP/O. So RP/O is the position of P relative to O. Now, we're going to define two quantities from that. The first one is we're going to define a quantity called the velocity of P. So VP, this is the first thing. VP in reference frame A is going to be defined as the velocity of P in reference frame A, and it's equal to the rate of change in reference frame A of the position of P relative to O. Now you'll notice something about the way I wrote the velocity. Notice that I did not write VP/O. I just wrote VP. It's because once I've measured the vector from O to P and I know that O is fixed in A, I'm taking the rate of change of that vector, but that rate of change is now giving me the velocity of point P, and as long as I am observing the rate of change in frame A, it doesn't matter where in frame A I'm standing. I can be standing anywhere, and that velocity is going to be the same. So I don't need the VP/O. The /O only arises from the fact that when I constructed the position, I needed to measure the position from a point. So I needed to know the point, and I needed to know the reference frame in which that point was fixed. But once I take the rate of change, I don't need to put VP/O. I can just put VP. So that's the velocity in reference frame A. And then next, we're going to define the acceleration of P in A. And that's going to be denoted A. That's the acceleration of P in reference frame A. And that's going to be defined as the rate of change in reference frame A of the velocity of P in A, which also happens to equal the second rate of change in A of the position of P relative to O. Now, I don't often use this second part, so I'm just going to put it in square brackets so that you'll know that that's what it is, but we generally do this in two steps. So we generally start with the position, differentiate it once to get the velocity, and then we differentiate that again to get acceleration. Now, what I need to do is I need to use this information, and we're going to start parameterizing motion. So this next topic is the one that's going to be pretty comprehensive in terms of trying to parameterize motion. And what we're going to be talking about is position, velocity, and acceleration of a point in commonly used coordinate systems. Now, the picture is going to be as follows. So I'm going to put the picture on the next page. So this is my picture. I'm going to start with the set of axes because it's just easier to describe all this through axes. Now imagine that I have a reference frame. I'm going to call that reference frame A. And imagine that I have a basis. I'm going to call that basis EX, EY, and EZ. And I have a point O, and O is going to be fixed in A. So O is fixed in A. O is fixed in A. O is fixed in A. And again, I have a point P. So here's my point P. P is an arbitrary point again. So P is arbitrary. Now, given what I just defined, which is the position of P relative to O, you see that here again I have the position of P relative to O. What I'm now going to do is I'm going to decompose this vector in this basis EX, EY, EZ. And I'm going to define these components. I'm going to call this component X, Y, and Z. And I'm also going to put a stipulation on this basis. This basis, EX, EY, EZ, is fixed in A. So I have a basis EX, EY, EZ that's fixed in A. This vector, which is the position of P relative to O, is decomposed into three components along those three directions. This is what's called Cartesian coordinates. Cartesian coordinates. Cartesian coordinates are defined using three displacements, I should say three linear displacements along three orthogonal directions. Now, if you look back at the picture, you'll actually see that the position of P relative to O, when I describe it in terms of those three displacements along these three orthogonal directions, is equal to XEX plus YEY plus ZEZ. Now recall that the basis EX, EY, EZ is fixed in reference frame A. So if I take the velocity of P relative to O in A, which is, as I defined it, the rate of change in A of the position of P relative to O, if I'm viewing everything in reference frame A, it doesn't look like these three basis vectors are changing. So I get X dot EX plus Y dot EY plus Z dot EZ. And the only thing that's changing are X, Y, and Z if I'm taking the rate of change in reference frame A. And then the acceleration of P relative to O and A, which as I said, as I defined, is the rate of change in A of the velocity of P. Sorry, there's no slash O here. This is my notational error. Let's fix that. This is VP. And then there's no P slash O here. It's just the acceleration of P. So you'll see that this is equal to X double dot EX plus Y double dot EY plus Z double dot EZ. And that's all we need for Cartesian coordinates because the rates of change of the basis vectors are fixed in the frame in which we're taking the rate of change, so the only thing that changes are the components. So that's the description for Cartesian coordinates. The next thing we're going to do is we're going to add to this picture. So in order to add to this picture, I'm going to describe what are called cylindrical coordinates. Now, in order to do that, let's drop a couple of definitions first. So I'm going to say let Q equal the projection of point P into the EX, EY plane. So if I go back to the picture, let's go back to this picture. This is point Q down here. I'm going to call this Q. All right. Now, if you now use Q together with the following quantities, I'm going to say let R equal the distance between O and Q. And then finally, I'm going to define an angle. I'm going to define an angle theta, which is going to be the angle from EX to the direction OQ, and I'm going to define ER to be the unit vector along OQ, which means that the angle theta is the angle from EX to ER. Now let's go back to the picture, and we're going to start adding to this picture. So here is the distance from O to Q. I'm going to call that R. And the unit vector along OQ I called ER. The angle is theta. From EX to ER is theta. And given this information, I can now define a new basis, which is this. I'm going to say let ER be the first vector in a new basis, and let EZ be the third vector in this new basis. Now, given the fact that ER is the first vector and that EZ is the third vector, we know that the third vector crossed with the first has to equal the second vector, which I'm going to call E sub theta. So now I'm going to go back over here and I'm going to draw E sub theta. So if I take EZ crossed with ER, I get a new vector here, which is going to be called E sub theta. If I actually draw this picture, here's what it looks like. I have EX. So I'm looking down from the direction EZ. I've got EX, EY, ER, and then I have E sub theta. This angle here is theta, and this angle is also theta, and then this direction out of the page is EZ. Now you'll notice something, that this basis that I defined, ER, E theta, EZ, is not fixed in A. So what I'm going to do is I'm going to say let B be the reference frame in which ER, E theta, EZ is fixed. So if I go back over to the picture, I'm going to add to this picture, and this picture is going to be as follows. Is that I'll go down here and I'll drop the notation ER, E theta, EZ is fixed in B. It's not fixed in A. So, given the fact that it's fixed in B, we need to also know a little bit about the origin, but because I'm using the same origin, O is also fixed in B. So O is fixed in both A and B. And actually, I'll augment to that in just a minute when I do the next coordinate system, but let's finish this one. So given that, let's look at the position of P relative to O expressed in the basis ER, E theta, EZ. If you actually look at it, the position of P relative to O is equal to the position of Q relative to O plus the position of P relative to Q. Well, the position of Q relative to O is equal to R times ER, and the position of P relative to Q is equal to Z, EZ. So this tells me the position of P relative to O is equal to RER plus ZEZ. Now, because ER, E theta, EZ is not fixed in reference frame A, I still want the velocity of P relative to O in A. But now I'm going to use this coordinate system, or this basis, that's fixed in frame B. So this is equal to the rate of change in frame A. Sorry, this is the velocity of P of RP relative to O. But because the basis is no longer fixed in frame A, it's fixed in frame B, I'm going to apply the transport theorem in order to be able to get the rate of change in frame A. It's going to be the rate of change of this vector in frame B plus the angular velocity of B in A crossed with the vector. Now, if you look at the picture back here, you'll see that the angular velocity of B in A, because again, let's look at this. EX, EY, EZ is fixed in A. ER, E theta, EZ is fixed in B. So if you look, you'll see that that theta defines the rotation between EX, EY, EZ and ER, E theta, EZ. And the axis of the rotation is the direction out of the page, which is EZ. So the angular velocity of B in A is equal to theta dot EZ. This is the angular rate, and this is the axis of rotation. So now that we have that, we can actually compute all these quantities. What is the rate of change in frame B of the position of P relative to O? Well, if I'm standing in frame B, the basis vectors ER, E theta, EZ are fixed in frame B, so the only thing that changes are R and Z. So I get R dot ER plus Z dot EZ. Now what about the second term? The second term now becomes the angular velocity of B in A crossed with RP relative to O. What do I get there? I get theta dot EZ, which is the angular velocity I just constructed, crossed with RER plus Z EZ, which is equal to R theta dot E theta, because the second term is 0. EZ crossed with ER is E theta, and EZ crossed with EZ is 0. So that tells me that the velocity of point P in A is equal to R dot ER plus z dot ez plus r theta dot e theta, which is equal to, putting the ordering back, plus r theta dot e theta plus z dot e z. Now, we're going to compute the acceleration. The acceleration of p in A is equal to the rate of change in frame A of the velocity of p in A. Now, again, we use the same argument we did on the position. Notice that this velocity is expressed in a basis that's fixed in reference frame B, but we want the rate of change in frame A. So this is equal to d dt in B of vpa plus the angular velocity of B in A crossed with vpa. So now let's look at d dt in B of vpa. What's that equal to? Well, if I'm standing in frame B and I take the rate of change of this velocity, vpa, the only thing that's changing are the coefficients. So I get r double dot er, and then the second term is a product. It's going to be r dot theta dot plus r theta double dot times e theta plus z double dot e z. And then also I get the angular velocity of B in A crossed with vpa is going to equal, now let's look at this. I've got theta dot ez crossed with r dot er plus r theta dot e theta plus z dot e z. So if I take this over to the next page, the angular velocity of B in A crossed with vpa is equal to theta dot, well actually we can just compute it now. So let's go back here. I got ez crossed with er is e theta, and ez crossed with e theta is minus er. So I get r dot theta dot e theta minus r theta dot squared er. So therefore, the acceleration of point P in A, which is equal to the sum of these now, let's add them. I get r double dot er minus r theta dot squared minus r theta dot squared er plus, and now you see that I have an r dot theta dot e theta, I have another r dot theta dot e theta, so I get 2 r dot theta dot plus r theta double dot e theta plus z double dot e z. Now if we look at this, what we actually have here is we have the same quantities we had in Cartesian coordinates, except for now we're expressing these rates of change in a different basis. So this is the velocity of point P in reference frame A, which is the same velocity we had when we were dealing with Cartesian coordinates, except for I'm expressing it now in cylindrical coordinates. The same thing here with the acceleration. It's the acceleration of point P in reference frame A, which was the same quantity I had when I was using Cartesian coordinates, but now I'm expressing the result in cylindrical coordinates. So this is what's called cylindrical coordinates. Now, cylindrical coordinates is actually defined. I should define them now. Cylindrical coordinates are defined by two displacements and an angle. And you'll notice that that's exactly what I have in an angle. You'll see that, what are the two displacements? The two displacements are r and z. Those are the displacements. and then theta is the angle. So that's how I define cylindrical coordinates. So the last set of coordinates that I'm going to go over in this video are going to be what are called spherical coordinates. Now, spherical coordinates require us to introduce some more quantities. So, first quantity I'm going to introduce is going to be this distance, which is going to be called rho. I'm going to say let rho be the distance from O to P. Not O to Q, it's O to P. Then I'm going to say let UR be the direction from O to P. Now, given the fact that I've defined a direction, I have to introduce a couple of other quantities in order to define a new basis. But let's go back to the picture first so I can start to describe this with a different color. So here's my picture. So now what I'm going to do is I'm going to say rho is the distance from O to P. So this distance from O to P, which I'm going to mark in red, is going to be denoted by rho. And then I'm going to let UR be the unit vector, which is the direction from O to P. And then what I'm going to do is I'm going to define another direction. I'm going to say that the second direction, or the another direction, I'm going to say let U sub theta equal E sub theta. Now the way I'm going to order this is I'm going to call the direction UR the first direction. I'm going to call U sub theta the third direction. So let's see what this actually looks like if we draw a picture. So a picture over here actually has UR looking like this. There's ER, there's EZ. This direction right here is going to be U sub R. And then this direction, which is into the page, is U sub theta, which I already denoted was actually the same thing as E sub theta, but what I really care about here is U sub theta. Then what I'm going to do is I'm going to define a vector. I'm going to define U sub phi to equal U sub theta crossed with U sub R. If I take U sub theta and I cross it with U sub R, I get a direction called U sub phi, which I can denote this way. And then I'm going to introduce an angle phi. Phi is going to equal the angle from EZ to UR. And that also happens to be the angle here from ER to U sub phi. So there's my picture for spherical coordinates. Now, again, I can do this early on just to make it a bit clearer. But spherical coordinates are defined by one displacement and two angles. So you'll see that in this particular case, my displacement, rho, is my displacement, and phi and theta are the angles. So I have spherical coordinate system. Now, given that, let's look at what I have here as far as quantities go. The position of P relative to O is defined by its magnitude and its direction. Its magnitude is rho because that's the distance from O to P, or the distance between O and P. The direction is UR because UR is the direction along OP. So now if I look at this, you'll actually see that the two rotations, or the two angles, make it so that this basis is now UR, U phi, U theta. If you actually look at the order. And you'll notice that it's not fixed in A or B. So what I'm going to do is I'm going to actually denote this frame. I'm going to say let C be the reference frame in which UR, U phi, U theta is fixed. So given the fact that it's fixed in reference frame C, we now need to apply the transport theorem between C and A in order to compute the velocity. So let's say I want the velocity of P in frame A. That's equal to the rate of change of the vector RP relative to O in frame A, which is equal to the rate of change in frame C of RP relative to O, plus the angular velocity now of C in A crossed with RP relative to O. So we need the angular velocity of C in A. Well, the angular velocity of C in A is going to equal the angular velocity of B in A plus the angular velocity of C in B. Now we've already computed the angular velocity of B in A. We have that. Now let's get the angular velocity of C in A, and we're going to do it using this picture. I'm going to redraw this picture a little bit bigger so that we can actually see what's going on more clearly. So here's this picture again, made bigger. There's ER, there's EZ, there's UR, and there's U sub phi. And U sub theta, which is the same thing as E sub theta, is into the page. Now, you'll notice that there's an angle phi that defines the rotation of this basis UR, U phi, U theta. So let's draw this again. UR, U phi, U theta is fixed in C, and ER, E theta, EZ is fixed in B. So from this, you can actually see that the angular velocity of C in B is equal to phi dot times the axis of rotation, which is equal to U sub theta. So now I have a way of being able to describe the angular velocity of C in B, which gives me that the angular velocity of C in A is equal to theta dot EZ. Actually, let's write it out. Omega BA plus omega CB, which is equal to theta dot EZ plus phi dot times U sub theta. So you see that that's a complete description now of the angular velocity, except I need to now transform EZ into the basis UR, U phi, U theta. So let's look at EZ. So you see that EZ has a component of cosine phi in the direction of UR, and it has a component of negative sine phi in the direction U theta because U phi, sorry. So this is negative U phi. So from that picture, I actually get that EZ is equal to cosine of phi times UR minus the sine of phi times U sub phi, which gives me that the angular velocity of C in A is equal to theta dot cosine of phi times UR minus theta dot sine of phi U sub phi plus phi dot U sub theta. And now I can use this information to start computing rates of change. So remember that the velocity of P in A is equal to d dt in A of the position of P relative to O, which is equal to d dt in C of the position of P relative to O, plus the angular velocity of C in A crossed with the position of P relative to O. Now, given the fact that I've just decomposed it again using the transport theorem, what is d dt in C of the position of P relative to O? Well, that's equal to rho dot times UR, because I don't have anything else going on in frame. If I'm standing in frame C, the only thing it looks like is changing is rho. And then the next term is I have omega CA crossed with RP relative to O. That's equal to, well, where's omega CA? It's theta dot cosine phi UR, cosine of phi UR, minus theta dot sine phi U phi, plus phi dot times U sub theta, crossed with rho UR. So now if you recall the order of the basis being UR, U phi, U theta, remember I said it's UR, U phi, U theta. So now, what am I going to get here? UR crossed with UR is 0. U phi crossed with UR is negative U theta. So I get rho theta dot sine phi times U theta. And then U theta crossed with UR is plus rho phi dot U sub phi, which gives me that the velocity of P in A is equal to rho dot UR plus rho phi dot U sub phi plus rho theta dot sine phi times U sub theta. So that gives me the velocity of point P in A. The next thing I need is the acceleration of point P in A. So the acceleration of P in A is equal to the rate of change in A of the velocity of P in A, which is equal to the rate of change in frame C of the velocity of P in A plus omega CA crossed with the velocity of P in A. Now look at this. Again, this vector VPA is expressed in a basis that's fixed in reference frame C, which is why I'm applying the transport theorem from frame C to frame A. So now let's actually take these rates of change. So the first one is going to be d dt in C of VPA. What does this give me? This gives me rho double dot UR plus rho dot phi dot plus rho phi double dot times U sub phi. And then I have plus, I've got rho dot theta dot sine phi plus rho times theta double dot sine phi plus theta dot phi dot cosine phi, the whole thing times U sub theta. So that gives me the first term. The second term is going to be omega CA crossed with VPA. That's equal to, let's go back and grab our angular velocity, theta dot cosine phi UR minus theta dot sine phi U sub phi plus phi dot U sub theta crossed with the velocity that I just computed, which is rho dot UR plus rho phi dot U phi plus, and and then rho theta dot sine phi u sub theta. So let's take this cross product, and what do we get? Well, ur crossed with ur is 0. ur crossed with u phi is u theta. So I get rho theta dot phi dot cosine of phi times u sub theta. And ur crossed with u theta is minus u sub phi. So I get minus rho times theta dot squared cosine phi sine phi times u sub phi. The next term is going to be u phi crossed with u theta. U phi crossed with u theta gives me minus u sub theta. Because of the ordering of the basis, it's the second cross with the first. So I get plus rho dot theta dot sine phi times u sub theta. And then u sub phi crossed with u sub phi is 0. U sub phi crossed with u theta is ur, so I get minus rho theta dot squared sine squared phi times u sub r. And then I have u theta crossed with ur. So u theta is the third vector in the basis. Ur is the first vector, so I get plus rho dot phi dot times u sub phi. And then I've got u theta crossed with u phi, which gives me minus rho phi dot squared times ur. So now let's start gathering up all the terms. I have the acceleration of p in A is equal to, let's gather up the ur terms. So the ur terms, I've got rho double dot, and then in this expression here I have minus rho theta dot squared sine squared phi, and then I have minus rho phi dot squared times u sub r. The next term is the u theta term. The u phi term. So let's look at the u phi term. I've got rho dot phi dot plus rho phi double dot, and I also have, let's see, I have another rho dot phi dot. So I have 2 rho dot times phi dot plus rho phi double dot. That takes care of these terms. And then what other terms do I have in the u phi direction? I've got minus rho theta dot squared times cosine of phi times the sine of phi, and that's multiplied by u phi. Now the last term I've got is the u theta component, which is the third contribution to this acceleration. So let's look at that. I've got rho dot theta dot sine phi, and I have another rho dot theta dot sine phi. So I have 2 rho dot theta dot sine of phi. And then the next term I have is rho theta double dot sine phi. And then I have, if you look at the term here, then when you take this rate of change, you see you got theta double dot sine phi plus theta dot phi dot times cosine phi. So I have a rho theta dot phi dot cosine phi, and I have another theta dot phi dot cosine phi times u theta. So I have plus 2 rho theta dot phi dot cosine phi, and then I have this term rho theta double dot sine phi, sine of phi, and then let's just see if there's anything else. So I have 2 rho dot theta dot sine phi plus 2 rho theta dot phi dot cosine phi plus rho theta double dot times the sine of phi multiplied by u sub phi. And that gives me the entire expression for the acceleration of point P in spherical coordinates, and this is a u sub theta. So that gives me the last term. And you can see that, again, an expression for the acceleration of point P in reference frame A expressed in this basis that I've defined as a spherical basis through spherical coordinates, which are defined through a displacement and two angles. So let's summarize this. So let's go through this. Cartesian coordinates are defined by three displacements along three orthogonal directions. That's the first one. Second one is cylindrical coordinates. Are defined as two displacements along two orthogonal directions and an angle. So you'll see here, this was x, y, z, which were my three displacements. Here we had r, theta, and z. Two displacements, r and z along two orthogonal directions plus an angle. And then the last one was spherical coordinates. Spherical coordinates are defined as one displacement and two angles. And that's rho, phi, and theta. And that's how we actually do calculations in these different coordinate systems that are fixed in different reference frames. So that's going to be it for this lecture. In the next lecture, we're going to go on, we're going to do some examples, and then we're also going to do some other definitions with some more coordinate systems.